So great, so let's get started. So everyone, so today we are moving on to the last two lectures in like the probability so overall theme. This will be about the central limit theorem and so convergence, and give us the probabilistic tools we need to be able to understand as we get more and more data how we're getting a better and better estimate, right? So so it's kind of developing the language we'll need to be able to describe this, and so that'll be the goal of these two lectures, and kind of understand the general properties that we have here. So let's look at the schedule. We'll do two lectures on this. And then we will move on to like the background linear algebra, and then we'll be kind of using that as the backbone of the rest of the class, but still relying on these ideas of probability. What's, I guess, two important things to notice on the schedule is that the first quizzes today. So at 10:35, I will stop the lecture. If you see me approaching 10:35 and I don't seem to realize the clock, please wave me down. So we'll stop the lecture, and then the quiz will be available on Canvas. You'll have until the end of the day to complete it, but 30 minutes once you start. I recommend you take it at 10:35. I will be around here and also on Zoom to answer any questions you might have about it. So again, some people will take the full time. That's fine. I think I aim for about the median time for a student to be about half of that time, but we'll see. If it's within about 5 minutes of that, I'll be okay. And then the other thing is the first homework is due next week on Tuesday. So I've got a number of a few questions about that. Most people seem to be getting most of it. The third question's a bit trickier. Again, let's just scroll up and look at the office hours. So my office hours are kind of after class. I've allocated time for at least half an hour, if not more, directly after class. And then Fridays at 9 o'clock on Zoom. And then the TA office hours are all clustered on Monday and Tuesday next week. The ones that are or MEB 3159 or Zoom are going to be in person. So next week. So if you need help, we have office hours set up. Canvas, ask these questions on Canvas. Don't say, is this the right answer? But other stuff about clarification, that's a great place to do it. It really kind of, you have a question, probably other people do too. And that's turned in as a single PDF through Canvas. So somehow convert whatever you've done into PDF so it's readable and we can easily grade it. The harder it is to grade, the more likely you are to lose some random points here and there, okay? So any general questions about the schedule and stuff before we get back to the lecture? So great. So without any further ado, as I say, let's talk about the sampling and estimation. Okay, and we'll get to the central limit theorem, which is kind of one of the really essential components of all of like statistical thinking, and will play, and it is at the heart of most of what happens within data analysis. We'll state a general version of it, not a specific version. And then in the next lecture on Tuesday, we'll see some specific versions you can actually use. We'll start with, we're going to get some data observations. Okay, and in this lecture, I'll try and stick to the notation in the book so this is clear, but we'll say that the data set will be a set P of points, P1, P2, up to Pn, okay? And I'm gonna reserve X for random variables. A lot of the class will use like X for the data, but today we'll be clear about that. These are data, so that these are data points we've gathered. So these are our observations, okay? And we're going to assume, we're going to talk about that assume that these are drawn IID from, some distribution. IID from a distribution, we'll call this F, okay? F will be a distribution because it's going to be a probability density function associated with the random variable. I'll kind of clarify that notation in a second. I first want to focus and highlight this IID. It should be IID. This is a term I had heard when I was an undergraduate and even when I was in graduate school, and I didn't know what it meant. And that was really frustrating. And Google has gone better, you know, but even then, this was something that was hard to put into Google and get an answer, and I was too embarrassed to kind of ask. So I mentioned on the first day of class, does anyone remember what IID stands for? I'll explain it. So this is very important. This is an assumption that underlies kind of almost all of data analysis, and it's often not explained. So this means identically and independently, so distributed. Okay, so identically, independently distributed. Okay, so let's break down what this means. So this means that okay, so the identically, if I can, there's a C in there. Okay, so this identically means each PI, each of the observations comes from the same distribution. From the same, let's do this over here. From the same distribution. Okay, and in this case, this distribution is going to be F, which I'll get back to in a second. Okay, so they're all, every observation I make, right? So if I'm getting a random observation, let's say I'm picking a random student from the U, I pick the UID number of active students. Every time I do that, I'm picking from the students of the U. Okay, if I'm making an observation about a bird I find in the wild and I record like I capture and measure how much it weighs and then I let the bird go, right? I'm capturing an independent bird from the wild. It's the same distribution. Now there might be some local factors that I want to pay into attention, but every time I make an observation, it's coming from the same process, and it should be somehow the same. I'm not drawing, okay, I'm going to draw one kind of student at the U who identifies as male, and then another student at the U who identifies as female, because I want to make it balanced in some way. For instance, or one person in their first year, one person in their last year, to try and balance all the data set. That's different from this. That's not what this is doing. Saying every observation is from the same observation. Anytime I pick someone, I make an observation, it could be anything, right? So I'm not kind of trying to force a balance or anything like that. Okay, so they're all from the same observation. Okay, the second part here, so independently. Okay, so this says that one observation does not influence another. Okay, so if I make one observation, like I pick a random student at the U, well, if I draw another random student at the U, it's the fact that the first person I picked had some characteristics does not affect what the second person I picked is going to be. In fact, I could pick the same person again, right? I'm no more likely to pick that person than anyone else probably, if it's a uniform distribution, but the first one is not affecting any of the other observations. There are sometimes we'll do kind of a set of samples, so without replacement. I don't think we'll do that in this course. It turns out most stuff goes through in that case, but in this case, we're going to just assume all the observations are independent from each other.
There was a question that had to do with the gender example.
Oh, yes. Would we have two sets of IID data, one from male, one from male? So you could do that, right? So you could draw a bunch of people who identify as male, a bunch of people who identify as female, two sets of IID observation. You'd build, then what we'll see is we'll take this data and we'll build a model based on the IID data, and we could build two different models if we wanted to do that. Yeah, but that's not what this is doing. So if you do kind of segment it, I mean, and there are other kind of more complicated ways to stratified sampling. That's not what we're doing here. Okay, everything is up. So we're not doing that example in this sort of class. If you were to do that, you'd have to run the analysis. You'd either have to build multiple models or somehow work out the dependence between the models, which just becomes much more complicated. And we're not going to do that in this class. You can do that. There are models which work into this. These are mostly kind of upper level classes in the math department, in the statistics classes there that deal with a lot of this sort of behavior. But that's not what we're going to be doing here. We're going to be looking at the simple form, and this underlies most analysis, as we'll see. So we're going to draw these points IID from a distribution F. Okay, and so that's what this means. It means they're all from the same distribution, and each data point is independent of all the other data points. We already used this independence pretty crucially in the last couple lectures, where we built this likelihood function based on a bunch of samples, and we assumed independence, and that allowed us to say the overall likelihood is the product of the individual likelihoods, right? Because then you can say something like, well, I want to be careful. I don't want to write something precise here because I want to be really careful about today, but we're going to have random variables associated with each of these, and then you can say a probability associated with each of those random variables is going to be independent of each other. Yeah, so what we can say is, it's based on independence, that the probability of, say, P1, P1, okay, I don't want to say this because, okay, so I want to be careful with notation about this today. Sometimes we'll be a little bit kind of loose with stuff to get the intuition, but these P1 through Pn, these are fixed now that we've observed them. Okay, once you've made an observation, there's no more randomness associated with this. Okay, so I don't want to write something about the product of seeing everything is equal to the product of the individual probabilities, which is essentially true. But I don't want to write that down here because I want to be a little bit more careful today. So in order to kind of talk about this more formally, we need to kind of talk about a random variables. Okay, so I'm going to associate a random so variable x. Okay, and this random variable x is going to have with a PDF f of x. Okay, and so this will be the distribution that we're drawing these points from. Okay, we're going to say that, so when we say this, we can say that a random variable is drawn from f of x, this distribution. So we're going to say that this is kind of a, this symbol is drawn from, right? So I'm selecting a random variable from this distribution. It's kind of implied when I write this subscript x in the f that there's a random variable x I can associate with this. So so what we're going to be interested in, we are now interested in the mean of f of x, right? The mean is going to be equal to, this is equal to the expected value of x, right? So if we have a distribution, this is f, then there's probably some point here, mu, we'll often say in mu, which is the mean of f of x, we would like to identify this mean of this distribution. Okay? And as we talked about the last couple lectures, if you draw a bunch of samples and you assume they come with Gaussian noise, then the mean is the most is the maximum likelihood estimator of these. Okay, so that's one reason why we might want to choose the mean. Also, it's kind of the expected value is just kind of a nice characteristic of this. Right? We've seen this multiple times now. So okay, so and we're going to try and do this by saying we've drawn all, or we've received all these observations. Okay, we've received these observations, again, P1, P2, up to Pn from f of x. And what's the most likely way to estimate the mean is what's called the sample mean. I'll call this P bar, which is going to equal 1 over n, sum over pi and p of pi, right? So just the sample mean. Okay, all the pi's now are constants. They're not random variables. Okay, these are observations, and so the sample mean is also going to be a constant. Okay, and often we would like to learn something about some underlying distribution, f of x, but we don't know what it is. We only get access to it by these observations of it, right? We get these observations of it, and we might get a sample mean. It could be that p hat is here, right? So this is not the true mean of the distribution. This is what we observed based on a bunch of these samples, right? I may have gotten a bunch of samples, and they happen to be kind of a little more of them on the right-hand side. So this end of the being biased to be a bit larger than what the right answer is, what the true mean is, right? It's the sample mean. Well, so we don't get the right answer. Okay, but this is a pretty good kind of guess of what the mean is, right? And we want to quantify how good this guess of the mean is. Okay. Okay. So the way to kind of think about this mathematically and the way to set all of this up is that we're going to say each pi is going to be a realization of a random variable xi. Okay, so this is now a random variable, right? So we have xi is a random variable, and this random variable is drawn from f of x. So there's an underlying distribution that somehow is modeling the truth of what is going on that we'd like to learn about. We can assume there's a random variable associated with it. And then each observation, PI, is a realization of that random variable. So the random variable, we don't know the outcome. The observation is when we actually figured out, we have observed one possible outcome. Okay? Okay, and we can, and then what we typically do is we say, well, this is a set of random variables, and these are drawn IID. So these are IID random variables that they're drawn. So this means that they're all independent from they're all each coming from this distribution, right? So they're this identical, they all come from the same distribution, and they're independent, they don't influence each other. And the independence is what allow us to say take products of the probabilities, or it will be crucial for the central limit theorem we'll see so next as well. Okay, and we get a set of this curly brackets indicate it's actually a kind of a like a set. So we're going to get a set of these realizations. Okay, and what we're going to do is we're going to process this by an average. Right, we're going to do this averaging operation, and we're going to get P bar, okay, out of this set. And so this is typically how the general structure of how data analysis works. There's some observation. We're going to model it as there's some distribution f of x. This is the true state of the world, filtered through however we've gathered the data. But we're going to assume we've gathered the data as every observation is independent of each other, and they're all identical from the same underlying distribution we're trying to learn something about. And we'd usually like to understand some sort of mean and expected value from that distribution. And we'll see the first example was, again, the single point estimator of, say, the average height, but we'll see more complicated examples of this throughout the semester. Okay, now we're going to talk about this next through random variables, right? And we'll see why we need to have this thinking about these observations, IAD, these random variables that are drawn from this distribution. And then those random variables are realized as constant, fixed observations, these PIs, and we typically are going to take something like an average. Okay, and as we'll see, we'll do more complicated things than averages. We'll build a regression model, we'll do clustering, but we'll also see that those are going to look kind of like averages, just over more complicated sort of models than single points. Okay, so this is the progression, and it's a little bit, so I think it's helpful to see it. If this distinction between a realization and a random variable is a bit confusing, most of the rest of the semester we can kind of blend them together. We'll just be working with the observations, and we'll we'll use this to understand why, as we get more observations, we get a better estimate. But for the next two lectures, this lecture and the next lecture in particular, it'll be important to have this talk about these random variables, which are still random. We haven't observed it. So we think about if we were to run this process and we haven't made the observations yet, then we have random variables. And we can say, well, how many observations will we need until we have a good estimate? Okay? Or we can say, well, we have estimates, but let's not look at them yet. And let's say how good approximation they are of the distribution. And then we can say, well, I corrected this p hat. How much do I trust it? Because I trust it based on the analysis we do of the random variables. Or we're going to run an algorithm that's a randomized algorithm that's modeling f of x. And every time we run it, we get an outcome of the algorithm. It does something concrete. That's an observation. But if we could run it, every time we could run in the future, it's modeling some random variable to output. Okay? So before we run it, it's a random variable. Before we observe it, it's a random variable. Once we observe it, it's a observation, or it's a actual data point. So to do the analysis, we need to talk about the random variables. To do the of how accurate it is, we need to do the random variables. But we actually get data, it's these observations. Okay, so now we're going to talk about random variables for this lecture and the next lecture, and then we'll the distinction will kind of not be right. It will not be essential to kind of get the gist of what the actual algorithms we're doing are studying later on after this. Okay. Okay, so now we can talk about the central limit theorem. And this is, at one time, this is the most important theorem in statistics. And another case, it's not actually just one theorem. It's probably hundreds of thousands of theorems. You could say, I proved a central limit theorem for this sort of setting. That might be something you would do, or you'd use one of them. So let me try and give you a general form, and then we'll look at kind of things that can be interpreted as specific versions of that we can use in the next lecture. Okay, so what we would like to do is we're going to think about a set of random variables. Let's say x1, x2 up to xn. And we're going to say that these are drawn IID from some distribution F. Okay, so that means this is IID of F. So each of these is done F. We know that the mean of this distribution F, this is a PDF associated with and random variables, is equal to mu, and its standard deviation of F. Actually, let's say the variance, typically written with the variance of F, is equal to sigma squared, and this is write this. This is bounded. So there are some distributions that have infinite variance, kind of really weird things that we're not going to deal with. So we're going to assume that the variance is not, you need to assume it's not infinite here, okay? So for instance, like the normal distribution or the uniform distribution over a fixed domain has bounded variance. If it was a uniform, a flat prior over all of the real numbers, well, that's an infinite variance. So we can't think about quite that. Okay, so now what we want to do is we want to analyze x bar, which is 1 over n, I equals 1 n, xi. Okay, so this looks like p bar, right? P bar was our sample mean. Now I'm doing this with random variables. Okay, x bar is again is not an observation, it's another random variable. So I can talk about the probability of x bar. Okay, and that's what I want to do. This will allow me not to just talk about the probability of one observation, but about the averages of observations. If I were to kind of realize all of the xi's and then compute all the pi's and then compute their average, that'll give me p bar. P bar is drawn from the distribution of x bar, as it turns out. Okay, so I want to talk about the distribution associated with x bar, which is again a random variable. Okay, and the results are that, okay, let's see, as n goes to infinity, actually write it like this, and the limit as n goes to infinity, that that x bar, the distribution associated with x bar, this converges to a So normal, a normal distribution. Okay, so I can think about the PDF associated with the random variable x bar that converges to a normal distribution. This is the e to the minus distance from the mean squared, right? That distribution, it's going to look like that, right? That's what this is one of the reasons that this normal distribution is so special, right? In that we can, if we draw from any distribution, this distribution did not need to be normal. F, the original one, did not need to be normal, but the average will converge to a normal distribution. Okay, the second property, well, what normal distribution will it converge to? Well, we can say that the expected value of x bar is equal to the expected value of each of these xi's, which was mu, right? We had set the mean of f, the original distribution was mu, so what we wanted to estimate from f, right? So we want, if you draw one sample, it's an estimation of the mean. It's trying to, we're trying to guess what the average is. But the average of x bar is the same. It's got the same mean, so that's good, right? So it's got the same expected value as if we drew from the full distribution. And then the last trait is that the variance of x bar, okay, is going to be equal to the variance of xi divided by n, which is sigma squared divided by n. Okay, so as we get more and more observations, what's happening to the variance? Yeah, the variance is getting smaller, right? It's getting more compressed. Okay, this is really good. This is really important. Also, it means that our uncertainty, how much this is the kind of the average squared deviation from the mean of what we observe. Well, if we draw and get a realization from this, is going to be smaller and smaller. So as we get more and more data points, the variance is going to go down at a rate which is linear. Okay, it's easier to think in the standard deviation. So the standard deviation of x bar, this is going to go at the rate of sigma divided by what? By square root of n. So the standard deviation doesn't go down as fast, it goes down at square root of n. So if you make 100 observations, it goes down at a rate of like 1/10. But the variance goes down faster. The variance is a squared quantity. This is in the same units here. So it's going down at the rate of the standard deviation, which is the quantity it's easier to picture, is going down at a rate of square root of the number of observations. Okay, so this means, okay, so what does this mean? That as we get a lot of observations, things look kind of normal. They in a formal sense, it's kind of the average of the random variables looks like it's coming from a normal distribution. Okay, it's got the same expected values we want, which is what we're going to want to estimate, and the variance is shrinking, so we're getting a better and better estimate. This is kind of a way of helping understand how, as we get more data, how much our estimates so improving here. Okay, great. So let's see. I want to, yeah. Let's talk. Let's try and do this. There's a demo. This collab file in this week's line on the schedule. There's a collab file. I'm going to jump to this. Okay, and I'm going to show you a demo. I think this is kind of very mathematical. Let's see a simple kind of example with data here. Okay, and let me reload everything. We'll reload some plotting library. Matplotlib is kind of the basic plotting library. The second line allows it to kind of images to show up. I'm not sure if collab may have that by default now. And we're going to use some random library. Okay, what we're going to do is we're going to kind of we're going to make observations of X bar. Okay, we're gonna make observations of X bar, and I'm gonna make 30,000 observations. Okay, so if I just make one, it's hard to see that, the distribution that X bar is coming from. So I'm gonna make a lot of them so you can really see the shape of this. So we're gonna empirically observe it, and I'm gonna make them over, they're gonna be real values, but it's hard to kind of figure out to aggregate them by just looking at the real values. So we're gonna bin them into 100 bins. So we're gonna make a histogram over 100 bins to kind of see what's going on here. Okay. Okay, so this is kind of the meat of it. And we're going to, what I'm doing here is I'm going to take n. N is the number of single observations of X, of F that we get, that we're going to average. That's n here. And I'm going to change this. We're going to see what happens. Okay, so I'm going to create a sample mean from so I'm going to actually get these observations. We're going to see kind of what the random variables look like by this plot. Okay, and we're going to, let's see, we're going to run for a number of trials to aggregate this. And this is, a lot of this is machinery to aggregate them into these bins to draw this histogram. And there's nice functions in Python. Python is, if you haven't used it before, it's got a lot of stuff built in. So eventually I'm going to kind of accumulate these into this set of the bins that counts, and I'm going to plot it as a histogram and some title stuff here. Okay, the mean is, and I'm going to do number of trials, and I'm going to, each trial, I'm going to set a sample sum to 0, and I'm going to get a random choice, and I'm going to add it, and then I'm going to divide it by n, right? So I'm taking the average, right? So this line here is taking the average, this is adding stuff up. My random distribution here is going to be a uniform distribution over the bins. Okay, so this is a RAM choice. This is not. You see here, this is the output. I'm going to change it in a second here. But the output looks kind of like a normal distribution. Okay, it should look kind of like it, but let's try and convince you. I need to do this on here. Let me try and convince you that I'm not starting with the normal distribution. I'm going to change this to a 1. Okay, I'm going to run this again. Okay, so if I change it to, if I only take an average over one variable, that's not really an average at all. It's just one variable. It's basically a uniform distribution, right? So it should look totally flat at the top, but there's random variation here, right? Okay, so if I just take 1 as a uniform distribution, and you should see as I increase this number, it should look more and more like a normal. Turns out if I do 2, the shape you get is exactly this triangular distribution. It's the average of 2 uniform random variables. Let's see if it's not quite as easy on a iPad, but it can be done. Let's see, okay, 3. Okay, it's starting to look a little bit like a normal. It's still maybe a bit pointier than it's supposed to be. And okay, let's do this 5 and comment. Okay. With 5, it's going to look more like a normal. We saw 10. Let's do 10. More, and notice not only does it looking like a normal, it's becoming more and more narrow. I'm hardly ever getting a sample that's outside of 20 or 80, right? So that's out there. And let's go up to say 30. Okay, even with 30, it's even more narrow. Now it's kind of rarely, probably about less than 10% of the time, it's outside of the range between 40 and 60, right? The true mean of this distribution should be 50. And as I average more and more things, it gets more and more concentrated towards the mean. The variance, the standard deviation is going down. Right? Okay, so does this demo make sense where I'm going here? There's a number of kind of different loops and stuff going on here, but this is kind of a realization of the, so the central limit theorem. If I were to plug a different random function in instead of the uniform random function, it would still converge to look like a normal distribution. If I were to draw it from a different distribution there, the uniform is actually a pretty spread out one, so it's a bit slower than if I were to use one that was already more concentrated in this range. So, okay, so as we get more observations, our estimate is getting closer and closer. Yeah. Okay, so the line that says sample mean append that is calculating X bar. Yeah, well, it's calculating P bar, right? This line that's here, when I calculate it on real data, it's not X bar anymore, it's P bar. So these are observations. These are not like random variables anymore. These are the observations of it. So that's one. Every time I do that, I get one data point. I'm doing it 30,000 times, and I'm plotting the histogram of it. So good. So okay. Let's see. We got about 10 minutes left. Let's see what we can get through here. Okay, there are probably a few remaining kind of mysteries about this that I haven't really specified, right? If I were to kind of prove, if I were like a probabilist or a statistician, I wanted to prove a central limit theorem, I need to be more careful about what it means to converge to a normal distribution. This is kind of tricky, right? Those plots look kind of like a normal distribution, but they weren't exactly a normal distribution, right? So how do we say it converges to a normal distribution? Okay, well, we actually are not going to talk about converging to a normal distribution in this class. So it's tricky, it's nuanced, and you know what? It's not going to matter too much. What we care about, it turns out, is exactly what I show in those plots. If you look at the tails, I want to say, well, what's the probability that, well, if the expected value is, say, 50, that I'm further than a distance 10 away from that? I'm outside of the 40 to 60 range. That's really what I care about. I care about the tails of the distribution. I don't care if the middle has some weird bumps in it or something, right? I care about how often do I get far from what I should be at. Okay, and that sort of notion of convergence will be more quantifiable, and that's what we'll focus on the next lecture. Okay, but there is a lot that's packed into this first statement, and that's where this kind of gets complicated. Okay, but we're gonna not deal with that much, so much. Okay. But if you're wondering what that meant, well, you'll have to take a different class. Okay, one of the other trickier things, okay, one of the things we're going to be kind of up against here is I'd like to say, well, I have an algorithm, or I collected so many data points. How accurate am I, right? I'd like to quantify, write down in some way how accurate I am. Am I missing anything in the chat?
It's still just confusion about the difference between like X bar and P bar.
Oh, okay. Yeah, if you have questions, definitely ask. I'm sure other people have these similar questions. Yeah, so if I go back, remember P bar, when I cross this middle line here, I've actually gathered data and I have no randomness left. Right, so P bar is what I've calculated on the data I observed. X bar is thinking about an algorithm I'm going to run that's going to estimate this, but I haven't done it yet. So I want to know what is the distribution of the output of X bar. Okay, great. Okay, so I want to talk about how to measure error, right? So how to measure the error or the let's say accuracy instead here. So how do I measure the accuracy of an algorithm or process that is behaving in this way, right? They're going to behave this way. I get observations that's not, you know, there's some uncertainty to it. Okay, so I want to say, well, I'd like to say, you know, P bar is at most kind of epsilon. I'll typically use epsilon as a parameter. Epsilon for an error measurement, far from mu, right? So I'd like to say something like this: P bar is never more than a distance epsilon from mu, right? Right, there's some mu, and I make an observation, you know, P bar based on averaging a bunch of these observations. I want to say it's kind of, it's, if I have some range, kind of epsilon on either side, and I say P bar is always in this range. I would like to make a guarantee like this. So if you do an approximation algorithm in kind of in an advanced algorithms course, you might kind of learn about bounds you can write like this. I'm going to calculate something. It won't be exactly the right answer, but it's going to have to be close in some way. Well, I can't say this, right? I can't necessarily say this because there's really some underlying probability distribution, right, that looks like this, and there's some probability of going into this region in these tails out here, right? These tails might not be, so I can't say this. So I can't say this here, so let me cross this off. Okay, so I can't say that. Well, what else would I like to say? Well, I'd also like to say, say with high, let's say high probability, and I'll quantify this as 1 minus delta, where delta is now a small value. This is another parameter we'll talk about. High probability that P bar is equal to mu, right? So that with some high probability that I'm going to get that P bar is going to be exactly the right answer, right? So there are other randomized algorithms that you might see that talk about something like this, where if I, for instance, if I run, if you, if I, right, so if I take enough samples of someone, eventually I'm going to find, with high probability, eventually I'm going to take a sample with someone who's in this class from all the people at the University of Utah. Eventually, I will sample someone who's in this class with high probability if my sample size is big enough. Okay, but that's not really what we're doing here. We'd like to estimate the expected value, and this is going to be kind of a continuous probability. Okay, and so the probability of this is this probability is the probability that P bar is equal to mu is equal to 0, actually. So this one I also can't do, but I need to combine these two things together. Okay, so I somehow need to combine these notions together. I'm going to say with high probability, P bar is going to be close to mu. I need to combine these two ideas together, and this is kind of a bit more complicated. This is called, and we'll just, yeah, so I will, let me, probably approximately so correct. And this is called a Pac Bound, P-A-C, a Pac Bound. And I'm going to say this is going to look something like the probability that X bar the distance from the true expected value of X bar, remember this is mu, this distance, right? So I can use just the absolute value here of the deviation from the probability that it's greater than epsilon. Remember, this is the same epsilon distance error parameter here. Okay, the probability that this is less than delta. Right, this is the probability of incorrectness parameter here. Okay, and that's measuring the probability. If I set an epsilon, then I can say that these little tails are less than delta. I have to combine these two notions together. I can't just say it has to be close or it's a low probability event. I say it's a low probability event that it's too far. And I have two parameters here, not just one parameter. And I have to somehow kind of combine these together in my kind of analysis here. Okay, and so on next lecture, next week, Tuesday, we will focus on a bunch of examples on how to get bounds that look like this. And this is what machine learning analysis bounds and randomized algorithm bounds often look like. So we're going to try and get you comfortable with this notion. And this is how you quantify the central limit theorem in a useful way. All right, so I'll stop the lecture here. If there are questions about the lecture, we can ask, but I want to give you time for the quiz. Once people start taking the quiz, I'd rather you don't talk and ask lecture questions publicly. If you have a question, either come up to me or raise a hand, and me and the TAs will be around. If you're on Zoom,